Hi, welcome back to es346 Basic Thermodynamics. This is module 1.3 System Properties. The corresponding sections in the textbook are sections 1.3 through 1.7. Here are the three learning objectives from this module. At the end of this module, you will be able to define a control volume and a control mass. You will be able to differentiate intensive and extensive properties, and you will know about the state postulate. So in thermodynamics, we talk a lot about systems. And what a system is, it is a quantity of mass or a quantity of space. And so here I show three classic thermodynamic systems. So let's go ahead and look at the one over here on the upper left first. Here we have a piston cylinder system which can change in volume. This piston may go up or may go down, either increasing or decreasing the volume. Now if we assume that that piston is very tightly fitting, the amount of material inside here will not change. Therefore the mass would remain constant while the volume changed. Since there's no other holes inside of this piston cylinder, therefore we would call this a closed system, and this would be a control mass, because we have controlled the amount of mass inside our system. Now let's go ahead and look down at this second system down here, which is a nozzle. And material comes in from the left, it contracts down, and material comes out here with a faster velocity. Now material is continually moving through here, so if we want to analyze this as a thermodynamic system, what we would do is draw sort of an imaginary boundary around here. We've got two real boundaries at the top and the bottom, and then we would define where we determine the inlet and the outlet is. Since material keeps moving, we're going to keep our volume constant. So this would be a control volume, a constant volume, control volume. Now let's look at a third system. This would be a little bit more complicated because we sort of mixed the two of the previous. We again have a piston cylinder system that is going, well, here the direction shows it going up, so the volume could be increasing inside here. We also have a hole in our piston cylinder, and material is coming in. Therefore, the mass is not going to be held constant within this volume space. So what we can do is we can define a control volume. It changes with time, but it will always be on the boundaries here. So this is a control volume, but a variable volume control volume. So let's do an example. And so what I show up here in the picture is a water pump. And so there's a hose with an inlet to the water pump, and then there's another hose at the outlet of the water pump. So what I want you to do is take a second and think about this question. If you were to analyze this pump as a thermodynamic system, would it be best described as a control mass, a constant control volume, or a variable control volume? Well, the answer to that would be a constant control volume. The pump isn't getting larger and smaller, its volume remains constant. However, material is coming in and out, so the mass is not constant. So we would describe in thermodynamics this as a constant control volume. All right, let's go ahead and move on and talk about properties. Properties are a lot like dimensions that we saw in the previous unit. They're characteristics of a system, and we'll talk a lot about thermodynamic properties. They're thermodynamic characteristics. And I've listed a lot of properties over here on the left, and we saw several in the previous module. For example, we saw mass, and we saw temperature. I also show a couple derived dimensions here. We have volume, which is a length cubed. We have a density, which is going to be a mass per length cubed. And then I also have a pressure, which is also a derived unit. We'll look at that in a little bit more detail in a few moments. Now, if I look at this piston cylinder I show over here on the right, and imagine that this yellowish gas is my material, this gas has various characteristics or properties. It would have a mass, a volume, a temperature, a pressure, and a density. Now, in thermodynamics, we break the properties classify them into either intensive or extensive properties. And intensive properties are independent of the amount of material, whereas extensive properties depend on the amount of material. Let's look a little closer at that. So again, I have my piston cylinder system over here, and let's go ahead and look at these 5 properties here, determine which are intensive and which are extensive. So if I look at the mass, the question is Does it matter how much of this cylinder to determine the mass? And an easy way to do this kind of test is just to cut it in half and say, now my system is just the lower part down here. If I cut it in half, does the mass change? Clearly it does. I'm going to have 1/2 of the mass if I cut it in half. So mass is an extensive property. If we look at volume, again, if I cut this in half, the volume is going to be 1/2. That is an extensive property. If I look at temperature now, if I was to measure the temperature in the bottom or measure the temperature in the top, I'd end up with the same amount, same value of temperature. It doesn't matter where it is. So there, temperature is an intensive property. If we look at pressure, this is also an intensive property, very similar to temperature. It doesn't matter where I measure it or if I cut my system in half. Now keep in mind, I'm not saying push the piston down so it's the smaller volume. I'm just saying we'll just cut it in half. How about density? Which is that, intensive or extensive? Well, the answer to that is it's going to be intensive. The density of the material here would be the same as the density of here, regardless of whether I cut the system in half or not. Now you may wonder, why do we care about differentiating between intensive and extensive properties? And the reason is because of the state postulate. And this is going to be one of the strongest tools that you have in this class. The state postulate says the following. The state of a simple compressible system is completely specified by two independent intensive properties. So there's the key. I want two, and they need to be intensive. And that's why it matters to know whether they're intensive or extensive properties. There's a couple other words here I'll mention. Simple compressible, all the systems we'll be looking at in here will fall into that category. So you don't need to worry too much about whether it is simple and compressible. And we're going to return to looking at when properties are independent. They most often are independent, but there's times where they are not, and we'll learn how to identify where those are.